All right, so I apologize for not starting this earlier, but you can tell what we talked about earlier. If we're solving exponents, solving exponential equations, okay, we want to know if the bases are equal, then the exponents must also be equal. And that's how we went through this entire first problem. We had two bases that were the same, and because they were both 5, we knew that these two exponents had to be equal. And once we rewrote the problem, all we had to do was solve for x. So on this second example, I wanted to keep about the same idea. I want to know if the bases are equal. Are the bases equal? No. So can I use this rule if the bases aren't equal? No. Can I make them equal? What an excellent question. Can I force these to have equal bases? Yes. Somehow or another, yes, I can. So that's what we need to think about and what we need to figure out.
Oh, you can multiply by times 2 and it'll be 32. What?
Okay, I think I know where you're going. Okay, so we're going to try this to start with. I wouldn't write this down. But some people recognize immediately that if I multiply this times 4, then this will give me 16, right? And then they'd be the same? There's one problem with that.
You can't multiply the one side, not the other.
That's right. So that means I have to multiply this times 4. So that's going to end up, that's not going to end up helping a bit, is it? Not to mention, right here, I would actually have to follow my laws of exponents. And that's a 4 to the first. So it would really be 4 to the 5x plus 1 power. I don't think this is helping.
You can break it up.
All right. So we're going to go away from that. What do you mean break it up? I like the idea.
On this paper, instead of working on the left side, you work on the right side.
All right. I think where she's trying to go is this.
It'd be 4.
Does everybody recognize that 16 is the same thing as 4 squared? Does everybody agree with that? So what I'm going to do right here is I'm going to take this 16 out. Okay? I'm just going to take 16 out. And what am I going to put in its place? 4 squared. 4 squared is the same thing as 16, right? So I just took the 16 out, put 4 squared in its place. That was an equal swap. I don't have to worry about doing it to both sides. Because all I did was swap one number out. Now what it looks like, though, I'm going to have to rewrite this, is it's going to look like this. 4 squared, that's my 16. But isn't the 16 being raised to the x minus 5 power?
Power to power, multiply.
Exactly. Power to power, multiply. Thank you, Mr. Hass. So we've got, on the left-hand side, I haven't done anything. But on the right-hand side, what's going on right here? Power to power, multiply. So I've got 2 times x minus 5. Well, that's 2x minus 10. And most importantly, the whole point of doing all that was, are these the same? They are the same, aren't they? So I can now write down that these two have to be the same. So now I know that 5x has to equal 2x minus 10. And I can solve. So I think I will subtract 2x from both sides and get 3x is equal to negative 10. And then divide and get x is equal to negative 10 thirds. Now, I'll go to the calculator to check that, so if you guys will hold on a second. What we recognize on this second problem is we recognize that 8 is a power of 2, and 32 is also a power of 2. So, hopefully you recognize that 2 to the third gives you the 8, and 2 to the fifth almost gives you 1 over 32. It has to be 2 to the negative fifth, right? The negative exponent makes it the fraction. All right, so now we see that they do actually end up having the same base. So now I'm looking at the same base. So I'm just going to rewrite this. It's going to be 2 to the third power. That is also raised to the x plus 4 power. And on the right-hand side, I have 2 to the negative 5 power. That is being raised to the second power. Is there any simplifying you can do with this? You can multiply that out because you've got power to a power. So that's going to be 2 raised to the 3x plus 12. And on the right-hand side, you also have power to power to the negative 10. And why do we like this situation? Because these are the same base, aren't they? So since they're the same base, I can go down here and I can say 3x plus 12 is equal to negative 10. I don't even have to worry about the 2 at all. I don't have to worry about the 8 or the 32. All that's gone away. I've just got 3x plus 12 equals negative 10. And now it's an Algebra 1 problem. Subtract the 12 from both sides. 3x will equal negative 22. And then when you divide, x equals, I'm pretty much out of room here, negative 22 over 3. And while that's a pretty ugly fraction, it will work. Do me a favor, girls. I would like for you to do the right-hand part up here. I want you to put in positive 1 over 32 raised to the second power. Guys, I want you to come over here, and I want you to do 8 raised to the negative 22 over 30 plus 4 power. So we're going to check that work. All right? What about inequalities? Okay? Think about this inequality statement for a second. If 3 to the x is less than 3 to the 5th, what on earth has to be true? That's it. Then that x right there.
4 anything lower than 5.
All right. X has to be something lower than 5, right? Less than 5. So really, doesn't this look exactly the same as an equation? So don't you do it exactly the same? So let's just do this problem exactly the same. What do we notice down here? How can we make these bases the same? Change what? Change the 9 to 3 squared, right? And then that's going to be raised to the 2x minus 5. And what am I going to do with this 2 exponent and this 2x minus 5 exponent? Multiply them. So that gives me 4x minus 10 has to be greater than 3 to the 3x. And then what does that tell me?
4x minus 10 has to be greater than 3x.
Good, because these two bases are the same. I now know that 4x minus 10 has to be greater than 3x. And from there, it's straight algebra. I will remind you of something, though. Let's see, if I subtract the 4x from both sides, that gives me this. And how do you get x by itself?
Divide by negative 1.
Okay, of course you're going to divide by negative 1, and that gives me 10 is, oh, about half of you missed that. Exactly. I just wanted to remind you that if you divide by negative, you have to switch the sign. Okay, we're going to take this. This is what's called the APR. Okay, it's called the annual percentage rate. So if you're unfamiliar with that, you want to get that down. That's the annual percentage rate, but we don't want the annual. We want to change it to a monthly rate. First things first, let's use our compound interest formula as best we can. So A equals, this is from yesterday. P is my principal. Here, I'll write that down.
1 plus R over N to the N times T.
That's correct. And of course, R stands for the annual percentage rate. That's your R right here. N is the number of times compounded, and you can see the word compounded in the problem. And then T is time in years. And T is always time in years on these types of problems. Now I'm going to fill in what I know. I know that it is a $2,000 investment. I know it's going to be 1 plus, what is my APR here? 0.036 over 1, because it was annual, raised to the 1, because it's annual, times T. I'm just going to have to use the letter T because I never told you a time, did I?
No.
So in reality, you guys were asking about function versus equation. This is actually a function because I have two variables. And I'm going to rewrite it as a function. A of t, the amount in my account, is a function of the amount of time it takes in the bank. So the amount is a function of time. And I'm just going to rewrite that. 2,000. Now, can I simplify these parentheses? Yeah, that's divided by 1, and then it's plus 1. So that's 1.036 raised to the t power. Are we okay with that? All right. Now, what I've got right here is my annual percentage rate. Do you notice this is from growth rate and decay rates from on Monday? Remember, is this a growth or a decay? How do you know that? Okay, it's over 1, right? So it's definitely growth because it's over 1. Now, I asked you about the changing this to the monthly rate, and most of us immediately think to ourselves, divide by 12, right? I mean, and that's a perfectly logical thing to think. So for a minute, I want you to divide this by 12. Now, this isn't right, so you don't have to write this down. But somebody, get your calculator, divide 1.036 divided by 12. And what would the new rate be? 0.863 repeating raised to the t power. Now, look at this function and look at this function. Does this represent growth or decay?
Decay.
That's decay. So if I divide this function, it changes from growth to decay. There's no possible way this will work. So that's one reason dividing by 12 doesn't work for me. So even though it's our intuition is to divide by 12, it's not going to work. So I have to attack this a different way. Here's what I want to do. I want to use I want to just concentrate on this number for a moment. I'm just going to come over here and concentrate on this number. I'm going to have to come back to it later. I just want to look at 1.036. So I've got 1.036. Is that the same thing as 1.036 raised to the first power? Is that the same thing?
Yeah.
Everybody agrees it's the same. Okay, I'm going to change the 1. Is that the same thing as 1.036 raised to the 12 divided by 12 power?
Yeah.
Yeah, because 12 divided by 12 is the same thing as 1, right? So that's the same thing. Is that the same thing as 1/12 times 12?
Yeah.
That's still the same thing, isn't it? 1/12 times 12 is 12 over 12, and 12 over 12 is 1. So far I haven't changed a thing, have I? Even though it looks different every single time. And now what I'm going to do is use my power rule of exponents. And I'm going to wrap it up like this. Doesn't this mean power to power? And you multiply, and 1/12 times 12 is 1. So this blue expression is equivalent to this, isn't it? So what do you think I'm going to do with it? I'm going to take this, and I'm going to plug it in over here. Okay? So what does it look like when I do that? It looks like I'm going to run out of space, I think, over here. So I'm going to kind of go off to the side. It's going to look like 2,000 times, instead of saying 1.036, I'm now going to say 1.036 to the 1/12th power raised to the 12th power, and then all of that's raised to the t power. Right? Now, sure, well, no, I'm getting ready to get rid of it, though, because what is 12? If I have a power to power here, can I just put those together and say that's a 12t? Okay, so that's why I didn't bother.
But is that
No, if you had a right parentheses, you would have to have a left parentheses. And I would have just snuck it in over here. But I don't need it now. Okay? All right, well, can you simplify this for me in the middle? 1.036 to the 1/12th power. Use your calculator and help me out. What is that? Go ahead. Let me get that from you.
1.002951609.
All right. And it's actually irrational. There's probably more after that. Okay? But this is my monthly rate. All right? This is actually giving me my monthly rate. Now, it's over 1, so what is the actual monthly rate? Move the decimal 2, it's going to be 0.2951609, blah, 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 percent, right? So a little bit less than 0.3%. That's my monthly rate, okay? And we're going to go to the calculator. I'm going to show you that those two things are going to equal the same.